Hello, I am going to talk about fitting distances by tree metrics, minimizing the total error within a constant factor. I'm Mikkel Thorup, and I work with Vincent, Cohen-Addad, Debarati, Evangelos, Kipouridis, and Nikos Parotsidis, and they're all great to work with. We've worked on taxonomy, which is a hierarchical classification of species, which goes back at least to Plato and Aristotle. The nice example of taxonomy is sort of that of Linné for plant species. With Darwin, it took an evolution, it took on a new meaning where the different classes in the hierarchy actually represents ancient species, ancestors. And then the numerical taxonomy problem became you're given some distances, say genetic distances between species in the present, and now you want to compute a likely evolution of the past. So it's about fitting distances by trees. An evolutionary tree for some species S is an edge-weighted tree with leaf set S, and the past distance in T introduce a metric on S. And so what we want is we have some input distance or measured distance, and now want to find a matching tree, minimizing the sum of errors between the input distances and the tree distances. So here's an example, including my student Evangelos. And here we have some distances, and here we have a corresponding tree. And in fact, this tree matches the distances exactly. So we can look at the distance from the monkey to the elephant, and it matches up here. Over here, you see a hyrax, which is the closest relative of the elephants we have today. Now, things are not perfect. Evolution doesn't behave perfectly, and the measurements are not perfect. So that there could be some errors like this distance being a bit bigger, 450. In this case, there's no perfect tree. And in fact, this tree is still minimizing the sum of errors. So that's just the way things are going to be. And this is why we have this problem of trying this optimization problem. And the optimization problem, minimizing the total error, is known to be APX hard. So the best we can hope for is a constant factor approximation. The best positive factor we have is log n times log n by Island and Cherry-Carr, who wrote that determining whether a constant factor approximation can be obtained is a fascinating question. The question fascinated us, and we solved it finding a constant factor approximation. So, and that I'm going to talk about this. In fact, we're only going to work with ultrametrics because there's a general reduction from tree metrics to ultrametrics where we only lose a factor 3 in the approximation factor. So what is an ultrametric? It's a special case of a tree metric where all the leaves are on the same distance from the root. It also corresponds to this 3-point condition mentioned here. There's a lot of history on these different problems, but we're actually going to go more into the technical stuff. So we are solving the ultrametric by something called hierarchical correlation clustering, which is a generalization, and it's already implicit in the literature. So to define it, first, let's look at correlation clustering. So if we have a partition, the edges of the partition are those you get if you view each set as a clique. Now, the correlation clustering problem is you are given some edges, and we want to partition all the nodes so that the edges of a partition match the input edges. And by matching, we look at symmetric difference. This is a problem we already know how to solve within a constant factor, and we're going to use that as a black box. So here an example to make sure we all agree what we are talking about. Here's an input set of edges. Here's a sort of a set of cliques, so corresponding to a partition into these two sets of size 4 and 3, and then also a singleton. And we have lost this edge and this edge, but we have gained this edge. So the symmetric difference is 3. Now, for the hierarchical correlation clustering, first we say a sequence of partitions P1 through PL are hierarchical if the lower ones subdivide the higher ones. In the hierarchical correlation clustering problem, we are given again some species, and then for some different levels 1 through L, we have a weight for each of them, and then we have a different edge set for each level. And now we want to find hierarchical partitions that makes a weighted sum over all the different levels of the symmetric difference between the edge sets and the edges of the partition on each level. And it's not hard to see that this generalizes an ultrametric. But let's again just look at an example. So here we have the input. That's a bunch of edge sets here. And here's a potential output. That's a hierarchical set of partitions that nicely subdivide each other as we go down. And let's see how good it is. Well, here on the lowest level, we lost this edge. On the level above, we lost this edge and this edge. And on this level, there is no difference. Okay. And then we have to multiply by the weights, and that's how we compute the cost. And we want to minimize this cost. Our approach to solving this problem is that we first completely ignore the hierarchy, and for each level independently, we solve the correlation clustering problem. So this means that for each level independently, we find this partition Qt that minimizes symmetric difference between the edges of the partition and the input edges on that level. And we do that within a constant factor. Next, we solve the hierarchical correlation clustering problem on this special case where the edge set on each level is the edge set of a partition. And whatever is returned, that's what we are going to return as the input, as the output for the whole problem. And we claim that we have only lost a constant factor. So again, the issue is that since we work independently on the levels, the Q1 through QL, these partitions may not be hierarchical. We have not explained how we actually solve this special case of hierarchical correlation clustering. I mean, when we started this work, nobody knew how to solve any of this hierarchical correlation clustering within a constant factor. And we have to argue why the solution we get is also a constant factor approximation for the original problem. The last part is kind of easy. So again, we look at a level, we have an edge set, and then we have the Qt is a completely arbitrary partition, and PT is a restricted partition in the sense that it has to fit some kind of hierarchy. So we can generally do better with Qt than with PT. And if we don't care about losing a constant factor, this means that it's not much more expensive to look at the cost from PT to ET if we instead go via Qt. There are some details here, but it all works out quite simply. The more interesting thing is this new special case of hierarchical correlation clustering that we call the hierarchical cluster agreement problem. So we, again, for each level, we have some weights. That's not so interesting. But then we have some partitions which are not hierarchical. And now we want to find the best matching hierarchical partitions. Okay, so again, we just minimize the weighted sum of the symmetric differences between the input partitions and the hierarchical output partitions. The idea for solving this problem is to use an LP, and it will decide which of the clusters in the input we want to keep in a slightly modified version for the output clusters, output partitions, hierarchical output partitions. And this turns out to be a very nice problem to work on using the same LP as Island and Charaka did, but with this special input. So let's just review the formulation, the LP formulation. For every level, we are going to get some distances. And if the distance from I to j is 0 on some level, it means that the two species are together on that level. So again, I should say the distance have to be 0 or 1. Then we have triangle inequality. And in this case with 0, 1, this ensures that togetherness is transitive. So PT will be a partition. And 2, that's the one that says that the distance are decreasing up the level. It means that if two things are together in PT, they're also together in PT plus 1. So this ensures that we have a hierarchical set of partitions, PT. And then we have the cost function. That's a standard thing. If we have two edges from the input, if we have an edge from the input, then we pay 1 if the distance is 1, 0 otherwise. And conversely, if we have a non-edge from the input, then we pay 1 if the distance is 0. So we get an exact match. So this is just an IP formulation of the hierarchical correlation clustering problem. Now we do the usual LP relaxation. And then we look at this special case where the edges from each level come from a partition Qt. And this is the one we claim we have a very nice LP solution for. that only increase the cost by a constant factor. So to describe it first intuitively, we're using the LP distances to somehow clean up the input clusters. So we're sort of having two places here. So if we are within a cluster, an input cluster, then we say two things are very close if they're at distance 0.01. And that's sort of the good case, because there should really be a distance 0. That would be ideal. Also, if we have something on the inside, we don't want it to be too close to something outside, because it should be at distance 1. So we think it's too close if it's at distance 0.5. Now, the world is not perfect. There may be some errors, so we may actually keep this whole cluster. But now we have a case like this one, where the species 5 is too close to many things outside. Well, then the LP is paying a lot, and we kick out 5. We could also have that 3 is only very close to few things inside the cluster. And again, the LP is not doing too well, because it should be too close to everything. So we actually kick 3 out. And then we may have a case with so much trouble, because there's so many species that are ill-behaved that we give up the whole cluster. But in that case, the LP will also have paid a cost that's basically quadratic in the size of the cluster. So as I said, with this cleaning, the LP is paying a lot for the removed parts. Another interesting aspect is that if something resides inside the cluster, then it will be a distance at most 0.02, because even if 1 and 6 are not directly too close to each other, there will be some species that they're both too close to, and this are very close to, and this gets the distance of 0.02. So being even more specific, we have the usual definition of balls out to some distance y. Our input is some set of species S, and then these weights and some input partitions. And then we solve the LP generating a bunch of distances, and the cost of these distances is a lower bound for the cost of making a hierarchical solution. Because it's fractional, it's only a lower bound. Now we take one level at a time, and we look at the input clusters from QT. We take one of them, and now we say which parts to keep. And we keep a species if it is very close to half the cluster. And it shouldn't be too close to more than too many things outside. So more precisely, what corresponds to 1% of the size of the cluster. Okay, so you should be very close to half and not too close to too many things outside. If after having removed those species, you lost more than 1% of the cluster, then you discard it completely. So you just do this for all clusters. And this is how you involve all the different distances generated by the LP. And now you have cleaned these clusters, and these are the LP approved families. So it will be a subset of the input clusters, and some of them will have been reduced a bit, but not too much, never more than 1%. So within these clusters, the distance will be at most 0.02. I talked about that before. When we look at it, calculating a little bit back and forth, we'll see that there are not too many species outside a level LP approved cluster that are too close. If you have something in the input cluster that is not does not stay after the cleaning, the LP is paying something proportional to the size of the cluster. And a bit similarly, if there's something that's too close to a level approved cluster, then the LP has paid something which is proportional to the cluster size again for each such thing. Okay, so this is what we can amortize over when we do the rounding. Now we look at how we take these LP approved families of partitions and turn them into a hierarchy. So what's a hierarchy? A hierarchy is just a rooted tree, and the leaves are going to be the species. For every node in this rooted tree, we'll have two kind of clusters: a core cluster, which is shown as a shaded part, and an output cluster, which is somewhat bigger, but never smaller. Okay, the leaves just corresponds to clusters. They're both output and core clusters at the same time. The interesting thing is what happens on the higher levels. So we go through the levels and we take out one of these the LP approved clusters, and we create a root node U corresponding to it. And we start by saying that the core cluster is just equal to the cluster. So this is how we start. Then we look at all the lower roots. So because we're all the time building higher and higher in this tree, we're building the tree bottom up. We look at all the lower roots and we look at those where the core cluster does not intersect us. So that's 1, 2, and 3. In such cases, we cut out the output cluster of these roots. Okay, so these are taken away from CU. So 5 didn't affect us at all, but 1 or 2, we had this case where we did not include the core, but we did include some of the output cluster, and we lose that part. Okay, this is now our core cluster, and we start saying that's also our output cluster, but we're going to possibly expand the output cluster. And what we do is we take all the lower roots that intersect us, that was those we didn't take before, and we add their output cluster to us to get our output cluster. So we make them our children, and we include the output cluster like this. So this is how CU now looked. Okay, so this is how it now looks at the top. We had these roots from below. They just stayed the way they were with the same core cluster and the same output clusters, and then we have this new core cluster and new output cluster. And this is how we got the next level of our partition. And at the end, we just output all these partitions. So this is the pseudocode of the algorithm. And the only way the LP was involved was by giving us these LP-approved families. Now let's study what went on. So we claimed first, so how was it that we took the core cluster and made the output cluster? We added some things, and what is it we added? What we really added was the union of all the descending core clusters. And we claim we didn't add that much. We claim it's actually only 2% more. So to prove that, let's focus on the highest descending core cluster that does not intersect C. So the highest one here is the child and another child here. And then we go down, down, down until we find, for the first time, a cluster that does not intersect us. Since the LP distances decreases up the level, and since the core diameters at most 0.02, we do know that the blue ones here, that was the ancestors of the gray one below the C, they all intersect C. So the maximal distance from thing is C to somewhere in the blue stuff, well, that's at most 0.04. And the gray stuff intersect its parent. That's a definition. The cores have to intersect. So the gray stuff get a distance at most 0.06 from C. Okay, so all these things are what we consider too close to C. So by LP cleaning, we know that the total size of blue and gray is at most 0.01 times C. And now we apply adduction, because everything below that, even though it may be very, very far away from gray in LP distance, the weight is only 0.02 times gray. That's what we know by induction. So we conclude that blue plus gray is at most 0.02 times C. And we have a similar argument that says, well, or the same analysis also gives us that the LP pays a lot for these things. So it basically pays C times blue times gray, because these are things that are too close but outside. And it will also pay for red because the cost of that is dominated. So this is how much the LP pays. And every time we add something to a cluster, we pay at most 1 times the size of the cluster. So the things are kind of adding up very nicely. We have a similar argument about how we lose things, the same thing. So basically, this is the end of the talk, since we can't get into more details. I love them, but we don't have time. So I just want to emphasize that the main open problem left is, in my opinion, what happens with L2. So thanks to Island and Hierarchical, we know the approximation factor is at most the square root of log n times log n. And we don't know if it's possible to get down to a constant. I think that's a very beautiful problem to work on, but all our ideas for L1 appear not to work here. But it would be great if somebody could solve it. And that's the end of the talk. Thank you for your attention. Bye-bye.